Hello, my name is Ben Williams. Welcome to my Lab 3 Physics 2212. So for the introduction to this lab, the purpose was to model circuits using batteries, capacitors, and resistors, and to find how a capacitor charges and discharges over time, and find how the voltage across the capacitor differs over time when it's being charged and discharged. And we also wanted to use Ohm's law to find the voltage, resistance, and current at different points through the circuit, and we also measured it using ammeters. So the principles of this lab were the loop and the node rule. The loop rule, which says that the voltage in a closed loop is zero. The node rule says that the current going in is equal to the current going out of a node. And we also use the voltage and current formulas, so that's Ohm's law. And then we also use the voltage formula across the capacitor over time, and that's a function of time. So we found that the time to discharge and charge a capacitor is equal, and the loop and the node rule can be used to predict values in a circuit like this. So for the experiment findings for this first circuit that we built, we have two batteries in series with two resistors, one that's 100 ohms, the other that's 47 ohms. And what we would expect in a circuit like this is that the current would be equal throughout the whole thing, and the voltage should be the voltage drop across the larger resistor should be bigger than the voltage drop across the smaller resistor. That's what we see. So the current in both spots is roughly equal. There's a small discrepancy, but we're going to say it's equal for our purposes at about 0.2 amps, which is the calculated value. And then the voltage drop across the first resistor is at 1.9 volts. The voltage drop across the smaller one is 0.8 volts. And what we found when we measured the battery is that it should be 2.9 volts. So we would expect the voltage drop across the circuit across the two resistors to be equal to 2.9 volts. What we find is that it's actually closer to 2.7 volts, and that's because of the resistors in the wires that actually have, or sorry, not the resistors in the wires. There are wires that have some resistance that we don't take into account. For the second part of this experiment, we're modeling the voltage over time, and so the voltage starts at 3 volts as it moves across the battery. Then it's kind of used by the components. So as it goes across the first resistor, it drops about 0.8 volts. Then as it goes across the second, it drops about 1.8 volts. Then it goes back to zero. And we're kind of just ignoring the resistance of the battery, or of the wires in this case. And we also calculated the resistance, or the resistance of the resistors using our measured voltage and current. And so if you do voltage divided by current, you get resistance via Ohm's law. So we calculated 40 ohms for the 47 ohm resistor and 90 ohms for the 100 ohm resistor. And those are both lower than the expected value. And that's because, again, of the resistance in the wires that we don't take into account. We also made this RC circuit that has a capacitor in series with a resistor. And what we would expect in a circuit that looks like this with 47 ohms resistor, we would expect a function of the voltage to look like this, where it starts at 3 and then gradually goes to 0 over time. That's per this equation when we plug in 3 for the initial voltage and then 47 for this RC. So if we go to what we did in our experiment, we put a 10 ohm light bulb in this circuit instead of that 47 ohm resistor. And what we found was as the circuit charges, when it has battery put in it, the light bulb starts bright but then goes dim. And when it is connected to when the light bulb is connected just to the capacitor, it starts bright and then goes dim again. So we found that the charging time of the capacitor is 12.5 seconds, which is equal to the discharging time. You see in this graph that really it should ideally be longer, but the resistance might not be exactly what we expect it to be. So that's not necessarily true. So what if you charge the capacitor with no resistor in the circuit? It would charge instantly per that equation that we had in the last slide. But this does not happen in real life because there is some resistance in the capacitor, resistance in the wire, and resistance in the ammeter. So in real life, it takes much longer than in the predicted time. And so in conclusion, using the loop and the node rule, you can calculate the voltages, resistance, and currents at various points in a circuit. When the voltage of the capacitor starts at whatever it's charged to and slowly discharges over time. Thank you.